Finite State Machines. In this video, I talk about FSM Fundamentals, state encoding strategies like one-hot encoding, binary encoding, and so on, state definition in SystemVerilog, FSM Coding Styles, 1 block, 2 block, or 3 block. Then I talk about what we should do for default state assignments, whether we should use X value or a specific state. And finally, I compare different FSM style for UART transmitter. Codes are available in our GitHub repository. What is a finite state machine? A finite state machine is a computational model that consists of 3 blocks: next state logic, state register, and output logic. Next state logic produces the next state based on the current state and input. State logic stores the value of the current state, and the output logic generates the output based on the current state. Then it calls Moore machine, or generate the output based on the current state and the input, which is called the Mealy machine. If in your FPGA or ASIC design the output goes to output port, it's recommended to register the output. In this way, the output glitch is reduced. And also in the ASIC design, if your partition your design and different people works on different partition, and if the output goes from your partition to the next partition, it's recommended to register the output. So always you use combinational logic for input and sequential logic for output. In this case, it makes writing the timing constraint much more easier for your partition. State encoding strategies. Binary encoding is like normal counter. It starts with 0, then 1, 2, 3. For encoding 8 state, we need 3 registers, as you can see here. In one-hot encoding, only 1 bit is set and other bits are 0. For 8 state, we need 8 registers in one-hot encoding. In gray encoding, only 1 bit change. So if we go from one state to next state, only 1 bit change. For example, here the first bit change, and then the second bit change, and then only the first bit change, and so on. In gray code encoding, we need 3 registers to encode 8 states. And finally, the Johnson counter encoding. Johnson counter is actually a shift register. It starts with 0, then the ones come in and then goes out. Also in Johnson counter encoding, we need 4 registers to encode 8 states. This table summarizes the different state encoding strategies. Binary encoding uses the minimum number of flip-flops, but the combinational logic is complex. One-hot encoding uses the same number of flip-flop as the number of states. The combinational logic is simple. Gray encoding and Johnson encoding have limited applications. When your states are sequential and there is no skip or jump in the state, then gray or Johnson encoding may be useful. For example, when you go from state 0 to state 1, 2, 3 until to state 10 and then come back to state 0, there is no jump and no branch. If there is a jump or branch in your state, then the combinational logic for gray and Johnson encoding become very complex. For Xilinx FPGA, if the number of states is less than 32 bit, then one-hot encoding is used. The general recommendation is that let the synthesis tools decide on encoding strategies based on your design constraints. In the following slides, I use the UART transmitter for comparing different coding styles. Here, the finite state diagram is shown. It consists of 4 states: idle, start, data, and stop. And there is 1 output. To define the state in SystemVerilog, always use enumerated data type. So here we define state underline t by using type def enum logic 4-bit. In this example, I use a one-hot encoding and I define the 4 state: idle, start, data, and stop, same as the state diagram. Then I define the current state and next state as a state data type. The enumerated data type has several benefits. First, type safety. If in your RTL code you accidentally change the value of the idle, the tools produce an error. So you can find it and fix the bug. Also, it makes your code more readable. In addition to this, during the simulation, in the waveform, you can see the name of the state. So it improves the debugging. First, we start with 3-block coding style. In FSM, we have 3 components: next state register, and output logic. In this style, each component has its own block in RTL code. So in next state logic, based on the current state and the input, the next state is generated. In a state register, if reset is asserted, the current state is idle. In normal situation, the current state is set to next state. And in output logic, based on the current state, the output is generated. 3-block style has some advantages. First, there is a clear separation between different components. Also, it has predictable behavior because the RTL code has the same structure as the synthesis circuit. And our design is modular. Each component has its own block. 2-block coding style. Another way to write the finite state machine is to combine the next state logic with output logic. Both next state and output logics are combinational. The state register is like the previous example. And we combine the output and next state in one combinational block. So we use always underline com in SystemVerilog. In this case, based on the current state and input, the next state is generated and also the output is produced. Another way to do this is to combine output logic with a state register in one sequential block. In this case, the output is register. So in one always underline FF block, we define the state register and also output logic. Output logic depends on the current state and it generates the output. The advantage of this coding style is that the output is register, but also there is one clock cycle delay in output. 1-block coding style. In this coding style, all next state logic, state register, and output logic are defined in one large always underline FF block. Also here the output is register. As you already noticed in this example, the next state is not defined and it is omitted. Only we use current state. And the output is generated based on the current state. This coding style has several advantages. First, it's simplified design because we don't use 2 or 3 blocks, we only use 1 block. Also, it is much more easier to read for a small FSM. The disadvantage of this coding style is that there is a mismatch between simulation and synthesis. Synthesis tools are very smart that they can generate the finite state machine based on this coding. And this coding style is look like other programming like C or C++. One question remains to answer is that how to handle undefined state. Should we use X value or a specific state? As you saw in the previous examples, for example, here for default value we use a specific state. Here we use the idle state. Or here for default value we use 1. Also we can use X value for default statement. Which one is better? Some people recommend use X value for default statements because it has some debugging and synthesis advantages. During debugging, if your state jump to illegal state, you can see red color in the simulation waveform and you can immediately find the bug. Also, it has synthesis advantages. X value in synthesis means don't care. So the synthesis try to optimize your hardware and the final circuit is more optimized. Also, some people recommend using a specific state, for example, idle, for default statement. They argue that the X value is outdated and it used in legacy Verilog code. SystemVerilog offers unique and priority keyword for better optimization. Also, using X value in your RTL code introduce mismatch between simulation and synthesis. Simulation consider X value as unknown and synthesis consider X value as don't care. Also, using X value for default statement reduce the robustness of your design. In actual hardware, maybe because of the environmental noise, your state goes to illegal state. In this case, your circuit behavior becomes unpredictable. But if you define a safe state for default statement, your circuit behavior is predictable. My recommendation is that use safe state for default statements. In modern submicron technology, using X value maybe reduce a couple of transistors, but it doesn't have much effect on area or power consumption of your design. And also it reduces the robustness of your design. Always specify a default recovery statement like idle. So your circuit always have a predictable behavior. For comparison, I consider UART transmitter as an example and I develop different FSM style. 1 block, 2 block combinational, 2 block sequential, and 3 block style. All of this code use same test bench and same design constraint. As you can see, all of them use 29 lookup table. Some coding style use 26 flip-flop and other use 25 flip-flop. The main difference is that in some style the output is registered and this one extra flip-flop is because of that. Also for 1 block style and 2 block sequential style that the output is registered, the timing is better. As you can see from this table, independent from our coding style, the synthesis tools generate the best circuit. So the question is that should we use 1, 2 or 3 block for finite state machine? As you can see in the previous example, the quality of the netlist is independent of the coding style. The key takeaway here is that choose the style that is best for you and for your design, and always use the coding style that has more clarity. Take home message: what is the best state encoding? Binary, one hot, gray code, or Johnson counter encoding? The answer is that let the synthesis tools decide the best encoding based on your constraint. What is the best FSM coding styles? 1 block, 2 block, or 3 block? The answer is that there is no best solution. Based on your personal preference, the team you are working, and the design, choose the best one. What should we do for FSM default statement? X value or safe state? My recommendation is use safe state. In rare cases where you are limited by area or your timing is tight, you can use X value. In this case, the synthesis tools generate a more optimized circuit. Thank you for watching this video.